안녕하세요.
Hello, we are Sungjin Han and
Hyunwoo Kim.
students at Korea Christian International School. Today we're going to share our research on the topic
The environmental contribution of low-temperature plasma-based MB filter recycling.
Since the COVID-19 pandemic, approximately 3.8 billion disposable masks are used and discarded each day. Most of these masks are made from polypropylene, a material that takes about 450 years to decompose, which is a very long time. The disposal of these masks releases harmful substances like CO2, causing serious environmental issues. Moreover, once MB filters lose their electrostatic properties over time and become contaminated with viruses or bacteria, they become very difficult to reuse. As students aspiring to study biotechnology and industrial engineering, we began to explore how engineering technologies can be used to recycle masks efficiently. We identified low-temperature plasma technology as a promising solution. Our objective was to investigate whether this technology can restore the electrostatic properties of MB filters, thereby enabling mask reuse and reducing negative environmental impact by the disposal of the filters. Low temperature plasma is considered the fourth state of the matter beyond solids, liquids, and gases. It consists of ions, electrons, and neutral particles, and although it carries high energy, its low temperature allows it to treat mask materials without damaging them, making it ideal for functional restoration. Compared to existing methods, low temperature plasma offers significant advantages. Existing methods, including corona discharge methods, use high temperatures and high voltages, which can damage the filter and waste energy. For chemical treatments, it can generate toxic byproducts and harm the environment. In contrast, low temperature plasma minimizes physical damage, uses less energy, and even has been proven in multiple studies to have disinfection properties. These factors make it highly suitable for mask filter regeneration.
Before discussing the experiments, here's a quick overview of how MB filters work. The key function of MB filters is their electrostatic attraction, which captures fine particles or viruses, preventing them from entering the respiratory system. However, this electrostatic property fades with time and use, being unable to capture those harmful particles that negatively affect the respiratory system. To address this, we designed an experiment to restore the electrostatic performance of used MB filters by low temperature plasma. Let's go back to the experimental setup. We standardized the filter samples to 5 cm squares and divide them into two groups. The control group was preserved in a way that retained its electrostatic charge, which is a new MB filter. The experiment group was soaked in 70% ethanol for 5 minutes to remove electrostatic properties, simulating a used and discarded mask. To measure the restoration level, we use Super P carbon powder. The more powder that adhered to the filter, the stronger the electrostatic charge. This method was inspired by KSEF professor Ildu Kim's work on the rabbit mask. Since the Super P particles are larger than viruses and or fine dust, Their adhesion is an indirect indicator of the filter's ability to capture some smaller harmful particles. Please note that all our plasma treatments and measurements were conducted using high precision plasma processing equipment from Femtoscience. We tested 3 different types of plasma: atmospheric, RF vacuum, and LF vacuum plasma. Each type was applied with different conditions for gas flow rates, power, and exposure time to determine the most effective settings. We compared the performance of each treated filter to that of a new MB filter using Super P carbon attachment as the indicator. As shown in figure 1, the MB filter extracted from a new mask attracts a large amount of Super P carbon particles. This indicates that the filter's electrostatic properties are at their maximum level. In contrast, as shown in figure 3, the MB filter stocked in ethanol shows no adhesion of Super P carbon particles, indicating that it has completely lost its electrostatic properties. In other words, this represents a used or time-degraded mask filter that would normally be discarded. The core of our experiment is to restore the electrostatic properties of these ethanol-treated filters using plasma treatment and then compare their performance with that of a unused mask filter. First, we tested atmospheric plasma using argon gas. As shown in figure 4, at its optimal conditions, the restored electrostatic performance was only about 20% of the new filter. Additionally, the high gas and power consumption made this method inefficient for large-scale applications. While no filter damage was absorbed, the low restoration rate and poor scalability made this method unsuitable for commercialization. Next, we tested RF vacuum plasma. As shown in figure 6, at 200 watts, the filter suffered significant damage with no restoration effect. Even when we lowered the power to 100 watts, damage was reduced, but the performance was still very low. To some, RF vacuum plasma was limited by its high voltage damage to the filter material. Lastly, we tested LF vacuum plasma. Through various trials, we found that the best result came from the following condition of 100 watts, 50 SCCM of oxygen gas, and 2 minutes of exposure. Under this condition, as shown in figure 8, we achieved an 83% restoration rate, which is almost equivalent to a new MB filter.
To summarize, LF vacuum plasma was the most effective method. It restored electrostatic properties without damaging the filter and also required lower gas and energy consumption, making it economically viable. In contrast, atmospheric and RF plasma both had critical limitations in performance or safety in terms of physical damage on the filter and energy consumption. Our research carries not only scientific significance but also environmental value. If used, MB filters can be regenerated by low temperature plasma. We could reduce microplastic waste, decrease greenhouse gas emissions, and minimize resource waste. We hope our research contributes to sustainable consumption and waste reduction in the future. Thank you for listening to our presentation. We hope our research has shed light on a new way to recycle masks and reduce environmental impact using engineering and scientific innovation.
Thank you.
Thank you.